We've been talking about kinetics, and last time we learned how to write and solve rate expressions. We talked about the collision theory, where particles must hit one another with enough force to overcome the activation energy, and the particles must be oriented properly for an effective collision. Any factor that increases the likelihood of an effective collision will increase reaction rate. And one of those factors we mentioned was concentration. To better understand concentration, we introduced the concept of rate laws, and we learned how to write simple rate laws where you have one reactant only. So for example, if you had 3 moles of A reacting to form C, we learned how to write a rate law where you have the concentration of reactant raised to some power n, where n is the order with respect to A. What we're going to get into today is, let's say, for example, we have a reaction in which you have more than one reactant. We're going to learn how to write a rate law. Again, rate is equal to K, the proportionality constant, concentration of reactants raised to some power, and we start in the alphabet at N and we work our way backward. So N, M, L. And we figure out these orders from experimental data. So N is the order with respect to A, M is the order with respect to B, and L is the order with respect to C. And that's all written in your notes. Now, in the event, if you had this equation right here, and you had the rate law, let's say rate is equal to K, A, B to the third power, if a reactant is not in a rate law, then the order with respect to that reactant would be 0, because altering the concentration of C has no effect on the rate. So if a reactant is not in a rate law, the order with respect to that reactant would be 0, and altering its concentration would have no effect on the rate. The order with respect to A would be first, the order with respect to B would be third, and the other thing you can do is get an overall order. An overall order is the sum of the exponents. So in this case, 1 plus 3 is 4. Overall order is the sum of the exponents. And we are going to learn how to derive rate laws where you have more than one reactant from experimental data. It looks really, really tricky. If you're very meticulous in your setup, you will be extremely successful with it. And you will see this assessed on your quiz. This will be the last thing assessed on your quiz. Everything I said is here, and then I'll go over this last piece. I told you that if the reactant's not in the rate law, the order is 0 with respect to that one. N, M, and L, for your purposes, will be somewhere between 0 and 5 or 6. They can be negative. They can be non-integral. You won't see that this year. That's very complicated. We talked about N being the order with respect to reactant A, M for B, L for C. Overall order is the sum of the exponents. The way you figure out how altering a concentration affects the rate is that you look at the concentration that's changing when the other reactant concentrations are held constant. So you're going to hold all reactant concentrations constant except one of them. You're going to look at the effect of altering the concentration of the one reactant on the rate. And that'll be the key right here to doing this correctly. And I'll show you what I mean in the following example. The first one is already done for you. I'll walk you through carefully, and then we will do several together so that you can master this concept. The directions will always read something like this. It says, write rate law equations for each of the following based on the data provided. Each reaction was carried out, in this case, at 25 degrees Celsius. Here's my reaction. A and B are reactants, C and D are products. Why would neither C nor D be in a rate law? Do you put reactant concentrations or product concentrations in a rate law? Reactant. Okay, so that's one key difference between a rate law and a rate equation. We learned how to write rate equations last time where you had -1 over coefficient. This is different. These are rate laws. So what we want to do is we want to figure out the rate law. We're trying to figure out N and M, the order with respect to A, the order with respect to B. We figure out these orders from experimental data only, not from stoichiometric coefficients for a net reaction. What we have here is far more complicated than what we saw previously. Previously we had 2 experiments. Here we have 4 experiments. We have both reactants. You can see that their concentrations are changing. And we're going to look at the effect of the rate at which C is formed in molar per sec. It could be molar per minute. And I guess if the reaction was extremely slow, you could have molar per hour, but I don't know why you'd want to run that. It would take forever. Here's the key. Hold one reactant concentration constant and examine the effect of the other on the rate. And that may not make sense because it's so wordy. I look at the data, and there's no perfect place to start. It's whatever pops out at you first. When I look at this data, I see, for example, that B is constant in experiment 1 and experiment 3. That means B is not affecting the rate because the concentration of B in these 2 experiments is constant. It doesn't change. I can see here that A is tripled from experiment 1 to experiment 3. So I hold B constant, it doesn't change, and I can see that A gets tripled. One of them has to change or you're not looking at any effect. So A triples, yet the rate is constant because if I divide these 2, I get 1. And that's what's shown here. I'm holding B constant, I'm looking at the effect of A, and I'm using experiments 1 and 3, and I'll pop in 1, 3 here. Those are the experiments you're using, and when we solve these out by hand, you'll see what you need to write to really make it easy to follow your work and make it easier for me to grade. So we're going to look at the concentration. I'm going to pop this down a line because it's too hard to read broken on the page. Where'd it go? There it is. Let me see if I can move it. There we go. That was strange. Okay, oops. Little sucker. There we go. We'll just leave it right there. It's being temperamental. So we're going to divide the concentration of A in experiment 3 by the concentration of A in experiment 1. Rate of the third over rate of the first. Now we're going to plug those quantities in. We've got 0.3 molar over 0.1 molar raised to the n. Rate of the third over rate of the first. This divided by this is 3 to the n is equal to 1. N is equal to 0, which means you have 0 order with respect to A. Concentration of A will not appear in the rate law because the order with respect to it is 0. Now, anytime you have 0 order, you can just cross out that whole column because regardless of what you do to A, there's no effect on the rate. And that will be beneficial in subsequent problems. Here it doesn't really matter. If A weren't 0 order, you would want to hold it constant. You don't actually have to here, but we will. So A is constant in experiment 2 and 3. B from experiment 3 to experiment 2 triples. I typically put the larger quantity in the numerator so I don't have to play with fractions. So I'm going to do 0.3 molar over 0.1 molar to the m, because this is the second reactant, and I'm going to put this over this, which is 3, and that's what's shown here. I get 3 to the m is 3, first order with respect to B. And now I write my rate law. I showed 0 order for A here. You don't actually need that. So rate is equal to K, concentration of B, overall order of 1. This one's all written out for you, which is nice, especially if you have trouble deciphering your notes. I want to figure out the rate law, so I'm trying to figure out N and M. I know the rate law will look like this. And I'm trying to figure out the rate law. It doesn't matter what you start with. I just look at what pops out at me. And what I notice initially is that NO is constant in experiments 1 and 2. Chlorine changes. Something has to change. I can see from here to here chlorine is doubled. So what I'm going to look at is the effect of the concentration of chlorine on the rate. And I'm going to write down 1 and 2 because that's going to tell me what experiment I used when I go back and check my work. I'm going to have the concentration of chlorine in experiment 2. I don't know if you need me to write that out, or if it will be implied from just putting the quantity in. Are you okay with that, or you want me to write everything out? Since you're not answering, I'll write everything out. So chlorine in the second experiment over chlorine in the first experiment, second reactant raised to the m. Rate of the second over rate of the first. That's going to be 0.0510 molar over 0.0255 molar raised to the m. and that's going to be 4.55 times 10 to the negative 5 molar per sec over 2.27 times 10 to the negative 5 molar per sec, and that's going to be 2 to the m is equal to 2. What's m?
1.
1. So the order with respect to chlorine is 1. And sometimes I'll put it here so that I can find it at the end. Now I'm going to look at the effect of nitrogen monoxide concentration. So what do I hold constant? The chlorine here and here, right? So what two experiments am I going to use?
1 and 3.
Correct. And now I look at these numbers, I put the big one over the small one. You don't have to actually write this step out, it's not necessary. So we're going to have 0.0250 molar, and again I put the larger quantity in the numerator to the N, and that's 9.08 times 10 to the negative 5 molar per sec, 2.27 times 10 to the negative 5 molar per sec, that's 2 to the N, is equal to 4. So what's N? 2. Second order with respect to nitrogen monoxide. Now I've got all the pieces of the puzzle. Rate is equal to K NO to the second, chlorine to the first, and overall order here would be 3 is correct. So it looks really, really hard, but as we do more and more problems, I think you will be extremely successful with this type of analysis. So here we've got 4 experiments, and we have 3 reactants. Changing concentration, we're looking at the effect on the rate. One thing that pops out at me right away is that B can't be held constant. So I'm going to try and figure out its order right away to see if there's something about B that makes the problem a little simpler. So I want to figure out the effect of B. Where are both A and C constant? Where A doesn't change and C doesn't change? 1 and 2. So I'm going to look at experiments 1 and 2 because A and C are constant. B doubles. The rate doesn't change. So I've got 0.40 molar, 0.20 molar, so that'll be to the M. I've got 3.0 times 10 to the negative 5 molar per minute over the same. So I've got 0.4 over 0.2 is 2 to the m is equal to 1. So m is 0. 0 order with respect to B. If a reactant has 0 order, does altering its concentration affect the rate? No. So we can literally just cross this out. Changing the concentration of B does not affect the rate, so we don't have to hold it constant. For this year only, if you see a column that isn't constant, it's probably 0 order. Prove it and dump it. Okay, I want you to try and find the effect of A. You have to hold C constant. See if you can do that. All right, so to get the effect of A, which experiments did you select? Which experiments did you select? 2 and 3. You couldn't pick 1 and 2 because then A wouldn't change. If you ever get 1 to the n or 1 to an exponent, you've made an error. So you've got 2 and 3. We can see the doubling of A. And I will say this, super bright class, many of you going to AP. This is something you have to be able to do in your head without a calculator in a multiple choice situation. When the exponents are different, like -4, -5, so this is closer to 0 than that, it's easier to just think of this as 24 over 3. So you have 2 to the n is equal to 8, and n is equal to 3. So the order with respect to A is 3. Now we need to get the order with respect to C. So what experiments are we going to look at for the effect of C? We have to hold A constant, so we're going to look at experiments 3 and 4. We've got this over this, so we have 0.80 molar over 0.20 molar, and that is going to be to the L, and we've got 3.84 times 10 to the negative 3 molar per minute, and we've got 2.4 times 10 to the negative 4 molar per minute. We have 4L is equal to, I'm guessing that's 16, yes? So L is equal to, what's L equal to? 2 is correct. So I'm going to put a 2 there. And now I've got a rate law of rate is equal to K, A to the third, C to the second. Overall order there would be 3 plus 2 is 5. And that is how you write rate laws. I'm going to give you a crazy hard one to do. You wouldn't see anything so difficult on a quiz, but I feel like if you can do the crazy hard one, you can do anything. Before we do the crazy hard one, I want to show you how to analyze these more complex rate laws. We talked about simple analysis with rate laws when we learned them at the very beginning. This is a little more complex, but we'll do some analysis here so you can see how to work it, and then we'll try the really hard one either together or on our own, whatever you want, to see if we're understanding rate laws, and then you'll have the rest of the period to problem solve. We're going to look at the effect of a change in concentration on the rate using rate laws. Determine the effect of the rate in each of the following and determine overall order. Let's do overall order first. It's easy and we can knock it out right here. Overall order is the sum of the exponents. So for example, in the first, 2 plus 1 is 4. What would the overall order of the second rate law be? 6 is correct. 3 plus 1 plus 2. And the third one, 2 plus 3 plus 1 is 6. So overall order is easy. Now let's see if we can figure out what happens to the rate when we alter one or more concentrations. In the first one, we've got this, and it says A is doubled. I'll replace the A with the 2, and I'll square it. And B is halved, so I'll put a half in for the B. I don't do anything to C, so I'm not going to bother with it. 2 squared is 4. 4 times a half is 2. So I would say the rate increases by a factor of 2. Does that make sense? All right, I'll have you walk me through the second one. A is doubled. What will I replace the A with?
2.
And then I'm going to cube it. B is halved. I'll replace the B with a half. And C is tripled. So what will I replace C with?
3.
3. And I will square it. I've got 8 times 1/2 times 9. I'll simplify that till 4. 4 times 9 is 36. So the rate increases by a factor of 36. Try 3. You try 3. Try, try, try. All right, so A is quartered. I have 1/4 to the half. B is doubled. I have 2 to the third, and C is quartered. So I basically have 1/4 to the third power is 1/64 times 8 is 1/8. So the rate decreases by a factor of 8 is correct. Whenever you get a fraction less than 1, the rate will decrease by a factor of the reciprocal. So if you got like 2/9, the rate would decrease by a factor of 9/2 or 4.5. Analysis straightforward. You'll see one of these questions on your quiz too. All right, let's see if we can do this absolutely crazy problem, which is harder than anything you would see on a quiz. Do you want to do it together or you want to try it? You want to try? Okay. Please remember that you have to hold 3 of them constant and change the first one, or change one of them. So just looking at the data, see what pops out at you first, and give it a shot. take a look. And then if you need me to walk you through it, we can do it. So I looked at the effect of B in experiments 1 and 2 because A, C, and D were constant. I have third order with respect to B. I put a 3 here. To get the effect of C, I looked at experiments 2 and 5. From 2 to 5, this quadruples, but these are all constant. Order with respect to C is 1. I looked at the effect of A in experiments 2 and 4. A tripled, the others were held constant. Order with respect to A is 3. And then to get the effect of concentration of D on the rate, I looked at experiments 1 and 3. D is doubled. The rate quadruples. Order with respect to D is 2. Here's my rate law. If they asked for overall order, you would have 9. How'd you do with it? And again, this one is harder than anything you will see, but if you can do this, you can do anything. Learning how to write rate laws takes some time. It helps explain how concentration affects reaction rate. If you practice, you will master this concept. On your classwork, which I will give you the next hour to do, you already did 1 through 6. You can now do 7 through 19. 18 is a little tricky. You wouldn't see anything that difficult, but again, it's good to challenge the brightest kids in the school. 19 is a very good thought question, understanding the kinetics in regard to carbon monoxide poisoning, and to better understand why it is imperative that you do not start cars with closed garages, why you don't turn on generators in homes or garages. Classwork 7 through 19. If you take the time to do these now, you will master the concept before you leave today. This as far as the quiz goes. So hopefully you know how to write rate laws, how to interpret them, and with practice you will master that concept. Next time we will talk more about the factors that affect reaction rates, as well as learning how to draw and interpret reaction profiles. And we will look at the effect of concentration on reaction rate doing an iodine clock reaction in the lab. Questions?